Okay, so today we want to look at the spectral sequence of a double complex, and we want to determine what the differentials are, dr. Okay, so a double complex looks like this, and we will assume that it's a first quadrant double complex. And we can filter by P, okay? So this is K0, K1, K2, and so on. And so this is just review. I want to make sure that you remember all the formulas. Okay, so we have this inclusion. Which we sum over all P. Okay. And this we call C. This is the same thing, and this is D. Okay. And then the inclusion is I0, the projection is J0, and this gives rise to a long exact sequence that we write as a triangle. Okay, and these maps are IJK. Okay. And this is the first exact couple. A1, E1. And then, this gives rise to derived couples. Okay. So we'll get AR to ER. And each ER is just the cohomology of the previous one. Okay, and then okay, so we know that A2 is just I of A1. So in general, you have a sequence of subgroups. And the map IR is just I restricted to the subgroup AR. Okay, so that's the map I. Okay, so this J, that's also J1. Yeah, J is the projection, right? And now, so J2, okay, J2 of an element, say C, A, in A2. So by definition, that A is in A2, so it's I of some A1, and then J2 of I A1 is just J1A1. Okay, and then you take its class in A2. And so this is also J1 is J. A1 is an inverse image of A. Okay, so it's also given by this formula. So that's J2. And then K, well, K is the connecting homomorphism. So K is given by, now the connecting homomorphism will start with, say, Kp over K e plus 1. And that comes from Kp. And then you go up by D. And then this will come from Kp plus 1. Okay, so if you start with a class here, B, it comes from an element B, and then you take dB, and this is an injection, and so dB has to come from a dB here, right? And then K of the class of B is just the class of dB, the cohomology class of dB. Okay? But I mean, this looks like it's the cohomology class of an exact form. So shouldn't this be 0? Yeah. What is the problem here? It looks like you're taking the cohomology class of an exact form. So it should be 0. But then that would say that K is always 0. Well, you see, the problem is this. When you take the cohomology class, right, this is the, this is actually not the no, what is this? This is, oh, yeah, it's here, right? It's H of B. And yeah, B is in Kp. And little b is in Kp, okay? And this is part of B, right? B is the direct sum of quotient. So this is the projection to the quotient, okay? Yeah. So this is actually, is a class in Kp over Kp plus 1, okay? You have B in Kp and you take its quotient class. Now, so dB, yeah. Yes. Okay, but this dB, it's actually in Kp plus 1. So, right, and so this is the, it's, right, it's in H of C, so it is in H of this direct sum, and so it's, this dB is in Kp plus 1. But B is in Kp, okay? So this is not an exact form in Kp plus 1. So, okay, so this is not 0. So because, no, this is the homology here, okay? It's in this. This is the homology in here, okay? But this is not 0 because B is in Kp, okay? So B is in Kp, but it's not necessarily in Kp plus 1. Yeah. To be 0 in the homology of cohomology Kp plus 1, it has to be the D of something in Kp plus 1. Okay? B is in Kp, not necessarily in Kp plus 1. Okay. So that's why it's not exact. It's not exact in this cohomology group. Okay. It might be if this B happens to be, you know, if this happens to be here. Oh no, but I think we should like start because we have a double complex, so we can put B in a specific block, and right. So here we can, we can say B is in KPQ. We choose B to be in that block. So it's not in Kp plus 1, okay? And that's why this is not necessarily 0. Okay, so that's how we get K. K is just given by big D. Okay, what else do I have to review? Oh, yes. Okay, and then how did we define KR? Okay. So, remember the way we defined when you have an exact couple, right? You K prime of an element is just K of that element. So KR from ER to AR is defined to be KR of a class ER. You define it to be just KR minus 1 of E. Okay. You just define it to be the previous one, the previous K. Okay, so that's how we that's all the definitions. And all right, yeah, okay. So we're gonna start with a double complex. Okay, this one, and this we will call K. Let me see. This one we'll call E0. Okay, E0. E0 is just a double complex. Okay. And then last time we showed that right, yeah, that so you okay, so E0 is a double complex, but it is also a direct sum of all the columns. So the columns are Kp over Kp plus 1. And so it is also B. Okay? And then the first, to get this, right, we first take the cohomology of B. And with respect to big D, okay. But last time we showed that on E0, big D, because you mark out, everything to the right. So big D is, it's the vertical one plus the horizontal one, but the horizontal one will become 0 because you mark out by Kp plus 1. So it's just the vertical one. And so it's just minus 1 to the PD. And so that H of B, that's with respect to big D, is actually the same as H little d. And big B is the same as K. So yeah, so that's E1, okay? E1 is the cohomology. Yes. E1 is the cohomology of B. So this is E1. Okay, so that's what we showed last time. And then on E1, we showed that D1 is actually delta. So that E2 is the cohomology of E1 with respect to D1 is actually H delta of E1, and that's H delta HD. Okay. Okay. So that's from last time. Okay. Now, okay, today, now we want to figure out what E2 is. And so an element of E2 is, it's an element of H delta HD. So it would be the class of an element B, okay? First in the cohomology with respect to D, then in the cohomology with respect to delta. And such an element, okay, we have seen before, is represented by a zigzag, right? So B is here, in order for its class in H little d to be defined, it has to be a cocycle with respect to D. And then, yeah, so in order for its class in H delta to be defined, there has to be a C like this, okay? So it's represented by a zigzag B plus C such that dB equals 0 and delta B equals minus D double prime C for some C. And this condition is the same as saying that big D of B plus C, which is dB, D double prime B plus delta B plus D double prime C plus delta C. And this is 0 because dB is 0. This is 0 because delta B is minus D double prime C. And so you are left with just delta C. Okay? So that's what an element of E2 looks like. It's represented by a zigzag, so that big D of that zigzag is delta C. Okay? You know, not every element of K will define an element of E1 or E2 or E3, right? Because, I mean, to be in E1, to be in E1s, so this is defined if and only if dB is 0. So to be in E1, you have to satisfy this condition. To be in E2, you have to satisfy this condition. And to be in E3, there will be more conditions. First, it has to be in E2, and then, you know, there's some additional conditions. So we'll say that an element of K, it defines an element of ER, okay? If it defines an element ER, we say it lives to ER, okay? So, yeah. And so, definition. An element, say, A in K, lives to ER if it defines an element of ER. And so that element, you know, it's going to be a cohomology class many times, right? It has to be a cohomology class in E1 and then in E2 and E3 and so on. So we'll denote it by AR, okay? So it lives to ER if and only if this is defined. And So now we know the condition for an element to live to E2. uh, and yeah. So let's work out D2. The differential D2 from E2 to E2. Yeah. So let B be in KPQ such that it lives to E2. E2 is defined. Okay, now if it's defined, so it is represented by this zigzag. It's represented by this zigzag. By zigzag. B plus C. Okay. And now, okay, we want to calculate D2 of B2. Okay. Okay. By definition, D2 is J2K2, right? In an exact couple. So this is the definition of D2. But the definition of K2 is that it's K of the previous one. So it's K1 of B in E1. Okay? And then you take its class in E2. Okay. So that's the definition of K2. Okay, but K1 is just K. B1, that's just the class of B. So this is, yeah, so that's because K1 is K. And then K of B, well, we just did that earlier. K is given by big D. Oh, it's erased. Yeah, so K is given by big D. Okay. And before we do that, no, let's see. Yeah. So, yeah, so here, okay, B is in KPQ. Okay, so B is in the filtration KP. This is KP. And then C is in KP plus 1. And this class, that's the class in KP mod KP plus 1. So you can add C to it, and it's the same. Because C is in KP plus 1. Okay. So when you take the quotient class, C just disappears. And then K is given by big D. So let's start over here again. Okay. Okay, so now I have J2. K is given by big D. And then this, take the class in E2. Okay. And big D of B plus C is delta C. So this is delta C, okay? And take its class in E2. And then J2 J2 is J1 of I inverse delta C. Okay, now what does I inverse mean? You see, I is induced from this map. This induces I. So I inverse, it just means that, okay, you have something in, like say in KP plus 1, KP plus 1, something, and then you just move it into the previous one, the previous KP. Okay, so now we're looking at delta C. Delta C is in KP plus 2. Okay. But this delta C is also in KP plus 1, because we are filtering by P. Okay, so this is not in KP, but it is in KP plus 1. Okay, it's also in KP plus 2. Okay, so right now it's in KP plus 2, and this just means that you consider it to be in KP plus 1. Okay, so yeah, so it's the same element. It is the same element, whether it's in KP plus 1 or in KP plus 2, okay? And then J1 is just a projection Right. And so, yeah, this is an arbitrary P, right? So it maps KP plus 2 into H KP plus 1. Okay. Yeah, and this delta C is in KP plus 2. Yeah, yeah. Right, yeah. So delta C is here. And I inverse, it means the element here, you know, well, just a minute. Oh, yeah. We're doing I inverse. We're taking the element, I think, yeah. No, what we should do is this, because it's, yeah, well, I think this element is in both KP plus 1 and KP plus 2. So, yeah, so what we can do is we can write it as J2 of I delta C. Okay. It's right. Yeah. So it is in KP plus 1, but it's also in KP plus 2. So, okay, so I think we can do this, but let's ver let's verify this. Okay, let's think about that at home. And then, so then J2 is J of I inverse I delta C, and that would cancel. And J is just projection, so it's the same thing, right? So you get the class of delta C. Okay? Yeah. So that is D2. That is D2. This sequence of computations. And yeah, there is this step that we need to think more about. Okay, so the conclusion is that D2 is delta of the tail end. Okay, D2 gives me that element. Let me state that as a theorem. Yeah. So theorem. Oh, yes. But then you see, this C is not unique. Yeah. So we need to check that if you choose a different C, you get the same class of delta C. Okay. So, but that is not hard to check. So I'll put that down as an exercise. This V2 of B2 is delta C2 is independent of the choice of C. And then we have the theorem. Let me see. So let K be a first quadrant double complex. And then you start with a B. So B2 in B2 in E2 PQ. Yeah. Be represented by a zigzag B plus C. So that's a zigzag in K. Then D2 goes from E2 to E2 is given by D2 of B2 is the class of delta C. And then we can also say where delta C is, okay, because this is P plus 1, P plus 2, okay? So delta C has P degree, P plus 2, and Q is just one less, Q minus 1. Okay, yeah. So that's D2. Okay, now let's do another one. Let's do D3. Okay, once we do D3, then you'll see, how it goes in general. So I think maybe I'll ask you to do D4 in the homework. So let's do D3 right now. What is D3? Yeah. Okay. So the differential D3 um, um, okay, so first of all, we have to know when does an element live to E3? So an element B in K EQ lives to E3 if and only if, okay, it's represented by a zigzag with one extra term. So let's say B is here, and so D of B has to be 0, and then since it's in E3, okay, it lives to E2 also, so it has to have a zigzag like this. But to live to E3 means that there's one extra term. So, there exists C1, C2 in K such that you have a zigzag like that with appropriate degrees so that D of B plus C1 plus C2, okay, that will have many terms, but they will cancel and you are left only with the tail term. So if you write this out, what it means is that VB has to be 0 and delta C1 has to be minus D double prime C2 and delta C2 has to be minus D double prime C3. Oh, no, just a minute. So delta B has to be minus D double prime C1 and delta C1 is minus D double prime C2, okay? So that's the condition for it to live to E3. Let me see, it's gonna take a little time to prove this, so I think we'll just take a break now for 10 minutes, okay? Yeah, okay. It's good to have a break. Yeah, because I think I figured this out now. Yeah. So yeah, let's prove the theorem, okay? So an element B lives to E3 if and only if it can be represented by a zigzag like this. Okay? Now, if it lives to E3, then it lives to E2. So we know that we have a zigzag like this. And now the problem is we have to extend this one step down. But yeah, but the thing is like, we don't know that there's an element that maps to this, okay? Yeah. So, okay, but now we have to use the you know, that the condition, you see, if it lives to E3, okay, it lives to E2, but not only does it live to E2, but it has to be a co-cycle in D2, okay? In order to live to E3, D2 of this zigzag has to be 0. Okay, so let's write down that condition. let me see. Maybe I'll use this part here. So prove. So since, yeah, B lives to E3, okay? So its class in 2 is defined, and D2 of B2 has to be 0. Okay, and so because its class is defined, so there exists zigzag B plus C, okay, such that um, uh, so the class B2 and then you apply D2 to this is 0, and okay, and then this is what? This is B plus C D delta, right? And okay, and oh, all right. So D2 is just delta C. So delta C of D delta equals 0. And this 0 is 0 D delta, okay? So delta D C D, this class has, it has to be, yeah, okay. This has to be a delta boundary, right? So this has to be delta of some C prime D, right? For some C prime. Because its delta class is 0, it has to be delta of something. And so, okay, but this is the same as the class of delta C prime D. And so delta of C minus C prime D is 0. Yeah. Okay. So you see, what you know is that you have another element here, C prime. Okay. And if you look at C minus C prime, first of all, when you map it up, this is, oh, yes, yeah, because C prime defines a class in D, so you know that D of C prime has to be 0. And therefore, when you take D of C minus C prime, you get DC prime, D of C, and D of C is delta B. Okay, let's do D double prime. Okay, so d double prime of C. And you put a minus sign there, and that is delta B. Okay, so instead of C, you can replace it by C minus C prime. And then C minus C prime has the property that delta of it is 0 in D. So that implies that delta of C minus C prime has to be exact. So it has to be D of C2 for some C2. Okay? So there is a C2 here. Now, okay, instead of D of C2, we should do minus D double prime C2. Okay? And now you call this C minus C prime your C1. And so now you will have a zigzag. Okay? So now you have a zigzag with this property. Okay? Because delta of this is minus d double prime of this, delta of this is minus d double prime of C2, okay? Yeah, so we have found our C1 and C2. And so the important thing in this proof is that this C doesn't work because you can't extend it, but by subtracting the C prime, then you can extend it. Okay? Yeah. Okay, so this proves the theorem. So now we know what an element of E3 looks like. And now we can compute D3. And now it'll be very similar to what we did before. So D3. So yeah. Okay, so we pick a B like that. Yeah, so and so we do D3 of B3, and that is J3, K3, D3. That's the definition of D3. And then K3 is K2, B2. And that's the definition of K3. Okay. And you'll get something in E2, but you have to take its class in E3. Okay. And then K2 is K1, B1. K1 is K. Okay. Instead of B1, so here, that is in KP plus 1. It's in the, it's in the homology of, cohomology of that. Well, you have to take the direct sum. Okay. So in any case, because you're modeling out by Kp plus 1, you can add C1 and C2 because they are 1 over, so they are in Kp plus 1. Okay. And then that's given by big D. Okay, you just take big D of that. And then take its class. And big D of that, yes, is delta C2. Mm-hmm. Okay, now where is delta C2? Well, delta C2, well, J3, it has to go from A3 to E3. So delta C2 is in A3. And A3 is IA2, it's IIA1. IIA1 is IIH of C. Okay? And what the I does, you know, the I just, right, it just take an element here, and you view it as an element of this subcomplex, right? Let me see. So, yeah. So this subcomplex, Kp plus 1, is a subcomplex of Kp, and I is induced from I0, which just take an element, say, here, okay, and you view it as an element of this subcomplex. So it's the same element, you know, and this induces I. Okay, so it's basically the element doesn't change. You know, it's just that you think of it as in different subcomplexes. Okay, so delta C2, it's actually II of itself. Okay, yeah, and so that's why I can write it as J3 of so J3 II delta C2, okay, and then J3 is J, you know, I inverse twice. And so the I's will cancel out, and the J is just projection So when you take the class, it doesn't change. Okay? Yeah. Uh-huh. Yeah, so I can justify this step now. I can write delta C as II delta C2. Uh-huh. Mhm. And okay, so that, yeah, that gives you D3. Uh-huh. Okay, so now we have a theorem. D3 is given by uh, by delta of the tail end. Uh-huh. Yeah. Yeah, so D3 is given by this. Okay? And now I can state the general theorem. General theorem. Okay, so let K be a first quadrant double complex an element B in KPQ lives to ER if and only if it can be represented by a zigzag. So B, so C1 dot dot dot. Let me see, where does it go? When it's E3, it ends at C2, so this would be R minus 1 by a zigzag, B plus C1 plus CR minus 1, such that D of it okay, everything will cancel except the tail term. And D3 of B, it's not D3, DR of BR is going to be the class of the tail term. Okay? So that's the general theorem. Yeah. And so DR, it goes from PQ to, okay, where does it go? It goes here. So 1 to R minus 1, and then R. So it increases P by R, and it decreases Q by R minus 1. So it's Q minus R minus 1, so it's Q minus R plus 1. Okay? Yeah. So we have this. Okay. And so we'll stop here today, and then next time we can apply this, okay, to prove again the check-Deram isomorphism. This will be, I don't know, is it the third proof? We did it once using the tic-tac-toe lemma. We did it another time, using, just the double complex. Yeah, so this will be the fourth proof. We'll do a fourth proof of the check-Deram isomorphism using the spectral sequence.